Hello, I'm Gasman, and today I'll be showing you how to get started with size coding on the ZX Spectrum. The material I'm going to cover here should, I hope, be usable by people with no previous experience of the Spectrum or Z80 assembler, although I am going to assume you know your way around low-level coding in general, what a processor does, what binary is, what a stack is, that sort of thing. Now, there's a lot to fit in, so I'll jump straight in. The first thing you're going to need is an emulator. I won't get into the real hardware versus emulator debate here. This is my workflow, and if you don't like it, go write your own tutorial about it. I'm on a Mac, so I use Fuse, which is the default choice for Mac and Linux. You can get it for Windows too. It might not be the absolute best emulator on Windows, but it'll do fine for us. Now, like all the best 8-bit computers, the Spectrum boots into a BASIC environment. Spectrum BASIC is a bit odd because rather than typing in keywords letter by letter, there's a key combination for each one. Uh, and that's probably going to be pretty horrible if you haven't grown up with that muscle memory. So instead we will switch to the 128K machine, which comes with this boot menu where you just have to press enter to select the tape loader, and that way we can avoid BASIC entirely. Now, unless you're Russian, cassette tape is the standard storage medium on the Spectrum, and on an emulator that means a tape image file, a .tap file. So next we need an assembler. I use Pasmo. I like it because it outputs tap files directly. Another essential tool for me is ZMakeBas. This takes a Spectrum BASIC program written as a text file and translates it to a Spectrum binary. I'll be sort of putting these links up on my GitHub page, so you'll be able to check these out later. So yeah, so ZMakeBas, while we're writing our code in assembler, the tape loader expects a BASIC program to serve as the launcher, so this lets us create that without dealing with the Spectrum's own BASIC editor. And finally, to glue things together, I'm using a makefile. So here I'm building the Spectrum, the basic stub with ZMakeBas, then the machine code with Pasmo, and then sticking those together in one tap image. The tap file format has the nice property that you can just concatenate two of these together and the result is still a valid file. Again, I'll put all this code on GitHub so you can sort of check this out at your leisure. So before we start writing the actual code, a bit of tech background on the Spectrum. It's an 8-bit machine with a Z80 processor, which means it has a 64K memory map. The bottom 16K is ROM and the remaining 48K is RAM. The 128K Spectrum has more, of course, available through bank switching, but we won't go into that today. So at the base of the RAM at 4000, you've got 6.5 kilobytes of screen memory, which I'll go into detail in a bit later. Directly above that, you've got a bit of memory that's reserved for the basic program and other assorted bits of data for the operating system. And assuming you've only got a tiny basic program, that's all going to fit below 6000 or 25,000, depending on which base you like your round numbers in. However, in practice, you don't want to put your code below 8000. The RAM below that point is slowed down because the processor is competing with the video hardware for memory accesses. At the other end of the memory, at the top of the address space, we've got the stack, which grows downwards as you push values onto it. But since it's not great for your code to be sandwiched between the basic code growing upwards and the stack growing downwards, we can move that. The location of the stack is managed by a system variable named ramtop, and yes, Discworld fans, this is where Terry Pratchett got it from, apparently. And generally, we move ramtop down below our code so that we've got a fixed span of memory all to ourselves. And you can see that in the in the basic loader code. We start off with this clear 24999, which sets ramtop to 24999, freeing up everything above that address. We then load our machine code block and then call it. USR is the Spectrum Basic keyword for calling a machine code routine, and it's a function rather than a statement, so syntax dictates you've got to do something with that return value. Randomize is just the standard way of doing nothing with that result, just throwing it away. So now that we've got all that out of the way, we can finally start writing some assembler. So let's get started on this. So as I said, we'll compile our code to 8000 because that's where the fast memory starts, and I'll write the simplest possible program that does something, and that will be to turn the border red. So we'll load the A register with 2, which is the color code for red, and then we'll write that to port FE. So port FE that's the input-output port that does everything, at least as far as the Spectrum's core hardware is concerned. So that includes reading the keyboard, outputting to the speaker, the audio ports for loading and saving to tape, and outputting to the bottom 3 bits controls the border color. So we'll do that and then return to basic. So let's build that with this make file that we put together, and that's going to, let's quit the emulator first. So our make file is going to launch the emulator again, and if I load that with the tape loader, we've got a lovely red border. Exciting. So let's now take a quick detour into Z80 assembler. Obviously I'll only really be scratching the surface here, but hopefully I can at least give a taste of what it's like to program in and how to think in Z80. I guess it's kind of close to x86. They have a common ancestor in the 8080, and there's a fairly small selection of registers with differing capabilities and not much consistent logic to which registers can do what. You just have to learn the different cases. When you start out with Z80, you'll probably find yourself often writing instructions that plausibly might exist but actually don't. So to start with, you've got the A register, the accumulator, which holds all the results of your 8-bit arithmetic, so you can sort of load with that. That's LD, and then add 20 here, just all very simple. Then you've got a bunch of register pairs which you can either use individually as 8-bit registers, like loading just B on its own, and then doing some more arithmetic with that, or you can put them together as 16-bit register pairs, and then you can use that for things like memory addresses. The HL register pair is the most powerful because for every arithmetic or logical operation that works on A and another register, like add A comma B, there is an extra one, add A comma HL, that works on the memory content at the address pointed to by HL. You can also do a limited amount of 16-bit arithmetic, like add HLBC, where the result goes into HL, so it works as a sort of limited 16-bit accumulator. The other register pairs you can do memory lookups with, like load A DE, but not at the same time as doing arithmetic. B and C are often used as loop counters because there's a special instruction DJNZ, decrement B and jump if not 0, and if you've got a small loop that you want to run up to 256 times, you will load B with the loop counter, stick a DJNZ at the end, and then you're done. There's also a set of very nice block copy instructions like LDI, which copies the byte at HL to the byte at DE and advances both of those, decrements BC, and so that's rather a lot to do in one instruction. But and then there's the repeating equivalent LDIR, which does the same, but then just repeats until BC reaches 0. So this reinforces a bit of a standard pattern where DE is the destination address where your results get written to, and even if you're not using those particular instructions, you'll often find they fall into that standard usage pattern. So if you're doing the sort of classic table effect where you're looking up values from a table, doing some processing on them, then writing the result back to the screen, then typically HL will be hopping around all of those tables, pointing to the addresses you need. You'll be reading those and doing arithmetic on them in the A register, and then when you're done with that, you'll have DE pointing at screen memory where you will write back there, and then BC is your loop counter if you need one. Often you'll just say continue looping until E wraps round to 0, and then that frees up BC for other things, because 6 registers or 6 and a bit registers aren't really much to go around. So we've also got our flag register, which keeps track of whether the last operation gave a result of 0 or carried over, and also a couple of weirder conditions, so you can use that for branching. The rules for which instructions affect which flags are completely inconsistent. So an increment instruction like or a decrement instruction dec B here, that will affect the 0 flag but not the carry flag, whereas a 16-bit equivalent of that, dec BC, doesn't affect any flags at all. So you might find yourself writing this sort of code and then you'll spend ages debugging it because it just doesn't do what it clearly logically should do. So it's lots of fun there. So yeah, as I say, 6, 7, 8 registers isn't very much. We also do have a whole alternate bank of these registers, usually denoted with a dash, and there's a couple of instructions, XAF, AF and EXX, where you can swap from one bank to another. In practice, this isn't quite as useful as it sounds, because when you're sort of in the middle of a routine and you're going, oh, I just need one more register, then you'll try EXX and then go, oh, now I don't have access to those other intermediate registers that I was working with. But yeah, it occasionally gets you out of a tight spot. Pro tip, if you're using the alternate registers and want to return to BASIC, you'll need to make sure that HL- contains 2758. But usually we aren't returning to BASIC in a demo, so that's fine. We've also got the index registers IX and IY, which are very fancy because for every instruction like add, you can not only say add A and the memory address IX, but also add A and the memory address IX plus an offset of 5 or something like that. In practice, these instructions are kind of slow and big, so it's not something you want to use much in size coding unless you're really short on registers. Or maybe this sort of thing might occasionally come in useful, maybe if you're doing like a particle effect where each particle has a set of variables stored against it and you want to work on each one in turn and then advance to the next one. Anyhow, you can't really use IY anyway due to a bug in the ROM, because the basic environment always expects IY to be pointing somewhere specific in its own system variables, and while we're running our own code, there is still an interrupt routine from the operating system running, which still assumes that it's pointing to that spot, and if you tinker around with that, then it has a nasty habit of occasionally corrupting memory. You can override the interrupt routine, but that takes more code than you'll want to spend in a tiny intro. Or maybe it won't. Prove me wrong. And finally, there's some really specialised registers. There's the I register, which controls interrupts, which again I'm not going to go into, and the R register, which is constantly incrementing, and it's meant to handle refreshing dynamic RAM, which is sort of not very sort of meaningful to us on emulators, but in practice that means if you need a really cheap and not very good random number generator in your code, then this will do the job nicely. So obviously I'm not going to cover the whole Z80 instruction set in this session, but if I've inspired you to go further, I can recommend this book, Mastering Machine Code on Your ZX Spectrum. This is the one that I learned with. It's a classic book from the 80s, and For a 2021 demo scene audience, the learning curve might be a bit weird because on one hand it's aimed at basic programmers, so it starts off really gently on this is how you count in binary, this is what a logical OR operation is, but then because programmers in the 80s were total badass, it suddenly launches into, right, now we're going to use this stuff we've learned to build a game of drafts with a computer AI opponent. And this didn't assume you had an assembler either. You were expected to code on paper, converting to hex by hand. So it's a sort of book where there's lots of useful information, but it's sort of you also want to skim over the sort of really simple bits and the bits that go sort of really deep on stuff you don't really need. But one bit that you do want to read closely is Chapter 8, which introduces all of the Z80 instructions in turn. Alternatively, if you have the sort of brain that works better with a pure reference guide, then you will want this one, Programming the Z80 by Rodney Zacks. It's kind of the Bible of Z80. Well, to me, it's kind of the Stephen Hawking brief history of time of the Spectrum world. It's something you just have to own in order to truly be part of the culture, and whether you'll actually ever read it is a different matter. So both of these are available online as PDFs. Again, I'll include all the links on GitHub. Let's get something on screen, shall we? So the screen memory is at 4000, and I think the best way to explain this layout is by writing a program to poke to that. So let's start at 4000, and let's make a loop where we will write to each address with the Lovebyte of that address, so we can sort of see the bit patterns there. Then we'll do a halt, so that waits for the next interrupt, which is one video frame, 1/50th of a second. Then we'll inc HL and then loop forever. JR is jump relative, so that's just a 1 byte offset for whenever you're in range of that. Again, always useful to know in size coding. So let's compile that and set that running. There, so you can see that it starts off kind of as you'd expect with the sort of bitmap going from left to right, but then after it's done one line, then it jumps down 8 pixels to do the next one, and then it carries on to repeatedly doing that, jumping down sort of an 8 pixel span at a time until it's done 8 of those rows, at which point then jumps in to fill in the next pixel row down. And this all seems a bit weird, but it makes more sense when you realize that it's done this way so that within one of these 8x8 character blocks, which is the 8x8 pixel blocks, which is the standard character based layout of the Spectrum, you can always go down to the next pixel row by adding 256, and everything else in this bizarre layout follows from that. So since you've got 32 characters going across, 32 bytes, then 8 lots of 32 gives you 256 bytes, and then after it's got that far, then it's just in sync, it's ready to fill in the next pixel row down. Then you've got 24 characters vertically, so we've got kind of 3 blocks of these 8 character rows each, and then once it's finished filling in all of the bitmap memory, then we'll see it adding a splash of color, which is the attribute memory, the color overlay. So each of these 8x8 pixel blocks has 1 byte of attribute memory devoted to it, and this is apparently slower than I can talk, so let's wait. There we go. So now you can see it's filling these in, so one byte for each of these character blocks, and that is laid out as follows. So let's get that up. Let's make that a bit smaller so that we can see everything at once. So the bottom 3 bits of each square is the foreground colour, known as the ink. So you can see that incrementing from black to white as we go there. The next 3 bits are the background, the paper colour. So then you see that's going blue, red, magenta, and then the next bit after that designates the entire character block as brighter than usual. So both the background and ink go brighter, so you can see there. You see they've got this brighter white background and foreground for this bit here. And then at the topmost bit is this sort of flashing effect that alternates between the ink and paper every few frames, and why they thought that was a good thing to spend a bit on, I'll never know. So this is all fairly logical from the point of view of doing character-based graphics, but this weird out-of-sequence line thing is a bit annoying when you just want a frame buffer to draw onto. So I'll share with you this the routine which has been passed down through for Z80 programmers through the ages, which given a screen address in DE will return the address of the next line down. So that's so it's a very useful thing to have, but I think for most people starting out in Spectrum size coding, doing your effects in the attribute bytes is where you're going to get the most instant return on your efforts. So let's do a bit of that, shall we? So going back to our code here, we'll keep our loop that runs once per frame, but let's call it frame loop just to make that a bit neater, and we won't need this. So start by pointing DE to the attribute memory, and we'll run this for 24 lines. So let's start a loop in B there using our DJNZ instruction. And then within that we will loop over 32 characters. There isn't an equivalent of DJNZ for the C register, so we'll do it in a couple of instructions. Decrement C and jump to char loop. So now we've got our X and Y coordinates in B and C, so let's do sort of a simple sort of XOR pattern here. I figure that if you can get an XOR pattern up, then from there on it's just fancier algorithms to get plasma or tunnels or whatever else. That's where you can take over and do the fun stuff. So we'll XOR those together and write to our memory in DE and increment that to get to the next byte of screen memory, and I think that's going to be our finished XOR pattern there. So let's see how that's going, and since that's just running on top of a blank screen, then we're not seeing our nice XOR color combinations there. You can at least see there's something's going on top of the loading text there. So let's throw in a quick checkerboard pattern to fully sort of see what's going on with the ink and paper combinations. So back to the screen memory at 4000, we'll poke that with 55, which is the first half of our checkerboard, and copy that to the next address along. So do that for the first pixel line of the first 8 rows, and that will get us ready to drop in another byte on the second pixel row down, where we can put our second half of the checkerboard pattern, where we can copy that over, And then so now we've got 2 pixel rows done, so we can copy that down the rest of the screen. So let's go back to the beginning here. This might not be very size optimized, but it'll do the job. And copy that 2 pixel rows down, and now we want to copy that over the remaining 600 bytes of the top third, and then we've got another sort of 2 blocks which adds up to 1600. And while we're doing that, let's stick in a black border, because black borders are cool. So let's see if that makes our XOR pattern a bit nicer there. Yeah, that's looking much nicer. So, right, what else can we do here? Well, we've got access to all the routines in the Spectrum Basic ROM, and there's a lot of useful stuff that we can take advantage of there. Things like clearing the screen, scrolling up the line, making a beep, line drawing. Most of it not optimized for speed, but in the size coding world, it's all code you don't have to write, so you can't complain too much about that. And for finding out about those routines, your ultimate weapon is the complete Spectrum ROM disassembly by Logan and O'Hara, again freely downloadable. But the most interesting thing for us is floating point maths. The Tony Baker book has a chapter on this which is well worth checking out, but briefly, the Spectrum has a 5-byte representation for floating point numbers. There's actually 2 representations, one for small integers, which begins with a 0 and sort of looks like this, just your standard representation, and then you've got the actual floating point representation where you've got 1 byte for the exponent, 1 bit for the sign, and then the rest as a binary fraction. So the Spectrum ROM actually has its own mini sort of stack-based virtual machine that you enter with this RST28 instruction, followed by this sort of bytecode. I'm not going to attempt any live coding of this. Instead, I'll paste in a pre-made routine for building a sign table, which is exactly what I do for my my intros anyway, most of the time. So let's so that's first our sort of definitions for the bytecode, and let's see. So then where is this stuff? Okay, so we'll drop this in. So there's a couple of things to point out about this. The shortcuts for getting values in and out of the calculator. There are ROM routines for that, but calling them isn't the most efficient use of bytes. There's a calculator instruction for pushing an arbitrary constant with an encoding scheme for passing 2, 3, 4 or all 5 bytes. So if you're not too bothered about accuracy, as we aren't for our value of pi over 128, you can just give it 1 byte of that binary fraction and say that's close enough. Neon on the sizecoding Discord came up with a really nice Python script that will calculate these byte encodings for any number or expression you give it, and I'll put in the link to that. For getting the result out, I found that the best way is to write to a specific spot in calculator memory, which is a small area set aside in the basic system variables, and then use the forbidden IY register to read that back. As I mentioned earlier, the basic ROM places IY in a fixed spot within its system variables for its own purposes, so we can take advantage of that to do a bit of relative addressing. And since we forced that result to be an integer here, we know it's going to be this sort of simple integer representation here, where we can just pluck out the 3rd byte of the representation and get back our sort of integer sort of sign result. So let's breeze through that really quickly. So let's use our sign table to sort of do a bit of a horizontal displacement to our to our XOR pattern. So start by pointing HL at our sign table. We'll advance that every frame. We'll also want to advance it throughout as we go down, so we'll want to sort of push that and then recall that one just before that point, and then we will add that to our horizontal displacement here. So we just want to swap these round so we're actually working with the horizontal one. So add our sign to that, and then for each character, for each row, increment HL, increment L rather. So that should give us the horizontal displacement there. So let's see if that does what we want. So this is going to take a few seconds to pre-calculate because it's 256 signs for it to calculate, and this is basic after all. So yeah, and there we go. So I think we can call that an actual demo effect. And if we look at our tape image here, oops, wrong window, you can see that's 93 bytes, and in fact it's 91 bytes because this includes 2 bytes for the tape, the header byte and the checksum. So yeah, not bad for half an hour's work, I think. So hope I've inspired you to give Spectrum size coding a go. So I'll put up all the code and links on GitHub over here. And so yeah, thanks very much for listening, and enjoy the rest of the party. Cheers.